would like to welcome everyone to the fourth KIOS Distinguished Lecture Series. This time we're very fortunate to have with us a distinguished professor, Christos Cassandras, who comes from Boston University. Christos will give two talks. One is today, and there will be another talk tomorrow afternoon at 4:30. It's not going to be in this room, it's going to be in the building underneath Nero at, I don't remember the code of the building, but it's room 010. Okay, Christos is a very good friend of KIOS. He has been with us several times so far. He has received his degrees from Yale, Harvard, and Stanford, so he has gone through all great universities. I'm not going to go through all the distinctions and awards he has received. He has also served as a president of Control System Society, as editor-in-chief of Transactional Automatic Control, and several other awards. His research interests are in the control and optimization of discrete event systems. He has applications in manufacturing, transportation, smart cities. He's going to talk about us today about some topics, some of his research in this context of autonomous systems. His topics are very relevant to the research interest of KIOS. So it's going to be, many of you are going to see some of the, and get some inspiration, hopefully, from what he has to show. Without any further ado, I would like to welcome Christos to give his presentation. Thank you.
Thank you. I'll try to stand here because I have a loud voice and I can see what you can see also. So can you hear me way in the back? I think I am blessed with a loud voice, so I think it'll work out. So the main theme of my talk today is decentralization. Of course, we're all interested in multi-agent systems, and there's tons of applications in that area, and I'll talk about different applications, but really the big challenge is how to distribute, how to decentralize the control and optimization of these systems, mostly because of scalability. Everything's about networks. Networks become larger and larger, more nodes, more edges. If you cannot distribute the functions that you want to perform, okay, yeah. Thanks. Then you will not be able to get very far. So that's the main theme. When can we do it? How can we do it? And how well does it work? Of course, you can always decentralize, but then you pay a price if you don't do it right. Okay, so here's the main themes that I'll be covering. I'll talk about a unifying framework, in my opinion, based on optimization in order to address all sorts of different problems in the context of cooperative multi-agent systems. And I will classify those problems into two categories. The parametric optimization ones, which are going to be easier, they're more static, and then the dynamic optimization ones, which are the more challenging ones. Then I will address this question: when is decentralized control possible? And I will show you that in the parametric optimization problems, the easier problems, we can derive explicit conditions and explicit algorithms, and the decentralization is not such hard of a problem. Of course, finding the right algorithms and solving specific problems is always challenging, but answering the question, is decentralization possible, is not terribly hard. Okay, I'll just set my timer here. So in the dynamic optimization context, the problem is much more challenging, and I'll try to explain why intuitively and also how we can address the problem. And finally, I will concentrate on a class of all these very general problems that we call the persistent monitoring problem, and I will show you some fairly recent results we've obtained that even though it is not possible to completely decentralize, you can almost decentralize. And by the way, I want to emphasize that when I say decentralized, I mean recover the solution that you can get from a fully centralized formulation in a decentralized context. I don't mean just come up with something that's decentralized. I mean recover exactly the truly optimal solution that you can get from a completely centralized context in a decentralized one. Okay, so let's start with cooperative multi-agent systems. Why are they interesting? Well, we all know that it's because you can build all these networks of autonomous systems. They cooperate with each other, they perform various tasks for a common goal, and there's all sorts of applications, surveillance, persistent monitoring, search, smart buildings, and this will be mostly the topic of tomorrow's talk, what we call the Internet of Cars. Now, if you believe in the buzzword Internet of Things, think now of the things as being just the cars, then you get an Internet of Cars, and that's the sort of the holy grail of intelligent transportation systems these days. Okay, so here's problem one. Here's the first class of problems that I'd like to talk about. This is an environment, a general environment. If you come from a robotics, very physical type of background, you can think of this as just an environment, a physical environment, in which there are certain obstacles that may make the life of these agents that may move around harder. And if you don't like that setting, then you can think of these obstacles as just constraints, mathematically. Areas in which in this search space of an optimization problem, you're not allowed to find solutions in these regions. Now, every point in my space, X, has a property. Now, what is that property? I don't really care. It's just something that adds value. So if you want to think about maximization, you can think of every point X as having a certain value, a certain importance. If you don't want to distinguish between points, think of them as all having importance equal to 1, and we can still do all of our work that way. However, if you want to think of some points as being more important than others, then you would give them the value of this function, which is higher or lower. And for any configuration of these agents, which as you can see, I indicate them here as a network, just to show that, for example, this guy and this guy cannot communicate, but the other ones can. For any configuration which is represented by a vector S, where S is the locations of these agents, there's a certain reward that you can collect from point X. So depending on how these guys are located, they can extract a certain reward from this point X, and if I move them around, this reward will change. So this function right here captures the interaction between your agents, your resources, and the environment. And now I can formulate this very general optimization problem. So over all of the x's in my environment omega, I have the importance, the weight, if you wish, attached to every x, and then the reward that I can get by controlling where I put my agents, which is captured by this vector s, and my goal would be to maximize this integral. So this is the cumulative reward that I can get with weights attached to the points x, subject, of course, to various constraints, and this set F is a subset of my, what we call mission space, within which you can operate and you're feasible. And the problem would be to find the optimal state vector so that you can maximize this function. Okay, that's a parametric optimization problem in the sense that if I can solve it, all I do is I find points S in this space that solve this problem. This is in contrast to problem type 2, which is harder. In this problem, the easiest way of thinking about it is that you're moving your agents around all the time. Why? Probably because you don't have a lot of agents, your space is huge, so you need to constantly move around to perform tasks. The problem now is harder because there's a time dimension. So I have to add an integral over time, in this particular case over some finite time. Everything else is sort of the same. There's still this reward function and this value function attached to every point x, but notice that now I'm trying to control the movement of these agents so as to maximize this performance criterion. I still have some constraints, but I also have some dynamics now attached to how these agents move in this environment. Oh, and by the way, I can also add some dynamics now to my points here, because if I have a finite set of what people call targets or data sources, then maybe these targets have their own dynamics. So now I can formulate a dynamic optimization problem trying to maximize this criterion here, subject to agent dynamics and environment dynamics. And the problem is dynamic because I need to find now trajectories and I'm controlling over a function space. All right, so these are my two problems. Now, let me tell you examples of well-known problems that people have studied that fit this framework. The first one is the so-called coverage control problem, and I call this version of the problem active cooperation. What does that mean? It means that rather than immediately starting out by partitioning your space, I'm going to allow my agents to cooperate, to constantly move if they have to move, and cooperate rather than arbitrarily divide the mission space in advance, which I'll show you next. So in this case, if you look at this little picture, the idea is that there's a mission space over here. All this question must represent potentially interesting events, data sources that may appear at some point, but I have no idea where they are. So I'd like to position myself here so as to maximize the chance of detecting things. And this function over here indicates what we call the event density. So some points in space may be more important than others, and I'll indicate that with this event density function. If I don't know any way to differentiate the importance of the different points, I'll make this just a flat surface. So this is my general formulation, if you remember. So let me tell you what these two functions are. Well, the R of x is simple, exactly what I just said, this event density. You can attach any importance you want to point x or to different regions so that some points are more important than others. And what's this? Well, this is what we call the joint event detection probability. If you assume that every agent I has a certain sensing capability, which is captured by this function, the event sensing probability, that means that basically if you're close enough to a point, you can do a good job collecting data. If you get too far away, then you cannot detect anything, or you can detect it with very low probability. And this function over here is a very well-known function. It is the probability that at least somebody will detect something. And the cooperation, as you can see, is captured by this product function. And notice that this is not generally a convex function. It is a nonlinear function of the controllable parameters S. So this makes this a non-convex, challenging optimization problem. So this is how this coverage control problem fits perfectly in this framework. Now I'll call this active cooperation. This is to contrast it to what people call the Voronoi partitioning. There are other ways to partition your space. So this is the space that I have here. These are 5 agents, and each one of them has been given a region of responsibility, which is called a Voronoi cell. This is basically the definition of a Voronoi cell. It means that if you have an agent, for example, here, this agent is closer to every point in the Voronoi cell than any on one of the other agents. So what you're trying to do here is, again, you attach a certain importance to different points, but you value the positioning of your agents captured by this vector S in terms of the quality of sensing, which again indicates that the closer you are, the better the sensing quality. And again, in terms of my general framework, R of x is the event occurrence frequency, essentially the same type of event density that I had before. And this function over here, which measures interactions of the cooperating agents with the environment, is indicated this way. But notice that now my functions here are captured by this quality of sensing, which is given by this function f, if you're in the Voronoi cell, otherwise 0. In other words, if you're this agent over here, you're not allowed to interfere with what the other agent is doing in the other Voronoi cell. So there's this partition. And people use this because it's a simpler way to attack the coverage problem. I just wanted to point out that, as you might expect, the active cooperation here, where I don't have a partitioning, generally does better. So this is an example in which if you try to maximize the joint event detection probability using the Voronoi partition, you achieve this value, and you can do better if you do not arbitrarily distinguish yourself. My color coding scheme, which you'll see in some other pictures, indicate the quality of the coverage. So purple is the best. You don't see it a lot except when you're right on top of the point. It means that you can detect something with almost perfect accuracy. And by the time you get down to the greens and the yellows and the whites at the edges here, it means that you cannot detect anything. So generally, you'd like to see colors which are dark green, which are more than 50% probability of detection. So that's the coverage problem. Consensus. Consensus is probably the most overmined, overcovered topic, at least in the systems and control area of the last 15 years or so. It is, in the context of this framework, one of the easiest problems that you can deal with. So in consensus, you have agents, and the agents essentially exchange information with their neighbors, and the way that the state of an agent changes is captured by the average, the sum, of all the information that you get from your neighbors minus your own information, and the goal is to ultimately achieve equal states. So if you want to think of the S's as positions, this is a rendezvous problem. You'd like to get all the agents to move the same point. If you want to think of S's as simply states of the environment, what do I see, then you want to reach agreement, hence the term consensus. So that's what you want to achieve. Now, why is this an easy problem in my context? It is easy because if I start with this framework, and because people like to minimize in consensus rather than maximizing, I've changed this with a minus sign here. But notice that the only thing that matters in consensus are the agents, not the rest of the points in the environment. So the only points that matter are, in this case, these 4 agents. Therefore, the R of x is simply an indicator function, a set of indicator functions, which say the only points in this environment that matter are where the agents are, nobody else, which means that this integral collapses into simply this sum. And then as for the functions that I'm trying to maximize here, they are simply typically quadratics of this difference between the respective states that you'd like to get to 0. So the optimal solution is obviously when all of these are equal to 0, so the sum of all these quadratics becomes 0. But notice that once you work with these quadratics, this is a convex optimization problem. So it's a relatively easy problem. There's no concern about the environment because it's all just about the agents. So the consensus problem is actually a relatively easy convex optimization problem. Formation control. Well, in formation control, there's people who look at formations that they like and then they analyze them. And then another interesting question that I find interesting at least is, why are there some particular shapes that are better than others? So if you look at nature, like the way that birds fly, they tend to fly in these V formations or these sort of wing formations. And it's interesting to ask the question, why? What is this formation that makes this shape better than others? So there must be some optimization criterion that these birds, unbeknownst to them, have in mind. Of course, they don't know it, but from our point of view, we can view them as optimizing, as solving an optimization problem. I don't know what this optimization problem is, but surely there must be one. And then there's the issue of adaptation. What happens if, as you move through the environment, your criterion changes and you have to adapt? So there's an interesting optimization problem that fits against this framework. I'm not going to talk too much about it, but in the optimal dynamic formation control problem, you imagine that there is a graph associated with the formation, the configuration. There's usually a leader and then some followers. There might be obstacles again. And the problem becomes one which looks like this. It's actually a pretty hard, typically mixed integer nonlinear program. Why integer? Because you're now looking for an optimal graph. You're actually trying to find the optimal way to connect agents, say this way, to achieve a certain optimization criterion, for example, this. So if I wanted to solve a coverage problem, I would say, all right, if I put together a bunch of agents who are connected and they move as a team, what is the optimal graph, the optimal configuration that they should have? And in fact, in a paper that was recently published, we showed that if the problem is coverage, then the optimal graph is a tree, which is nice because trees are nice to work with. And therefore, this problem becomes much, much simpler because now that you know that this graph is a tree is simpler, and you can solve such problems. Okay, the Internet of Cars. So again, this is a multi-agent system where your agents are cars. What I'm showing you here is the map of a double intersection here and here, which is very close to my own office in Boston. So my office is, if you look at this map, is about here. and I live with this every day, every morning and every evening. It's one of the worst designed double intersections in the history of civilization, and it's a problem because if you come from this direction, this is what we call the BU bridge. It's a bridge, actually. For some strange reason, the city of Boston doesn't allow you to make a left turn. So you're forced to come this way, which is what I do every morning. You have to come this way. But when you come this way, this little road over here is fed from traffic from here and also from two roads that you cannot see. And then it goes right, left, across here, and across there. This area right here fits about 7 or 8 cars. So when this light is green and these cars move, very often they fill up this area. Then the light turns green here, these cars come, they get blocked. Here you can only fit another maybe 10 cars. And then you block this intersection. So if these cars want to come, they can't go anywhere. They block this intersection and you have a deadlock, a double deadlock. It's fascinating to see. And so what I show you here, and I'll show you the animation in a second, is this is the current situation with some traffic lights. And this is what we can achieve with a distributed, decentralized control where there are no traffic lights. You just simply control the flow of the cars just so that they don't hit each other. And it works. Of course, I have not been allowed to implement this in Boston yet, but at least in simulation, you can see what's going on. So if you look at the left, I'll talk more about that tomorrow. The important thing to note is, just eyeballing it, is that because of traffic lights, when the lights are red, there will be some congestion that forms. And when you see here, the scenarios are the same. You don't see this congestion. If you look very carefully, and tomorrow I'll call your attention more to that, you will see, well, it stopped, that what we control here is we control the acceleration and deceleration of cars. So when a car from here and a car from here come, we just control their acceleration just so that they go through without hitting each other as fast as possible, and we achieve maximum throughput and maximum energy. So one of the new criteria that we want to consider in these problems of multi-agent systems is energy. We'd like to minimize the energy because that way we reduce fuel consumption, emissions in the environment, and everybody's happy. So we'll talk more about that tomorrow, but I just wanted to point out this is another example of a multi-agent system. Okay, related work, there's lots. I just pointed out here a few sample papers. There's a lot of people that are working on the coverage control problem, formation control, consensus. There's a lot of people that talk about distributed estimation and tracking, and I'll talk more about the persistent monitoring. Here are the challenges in the I mean, if you decide to work on multi-agent systems, you have to address all these 5 issues. The first 2 really are the ones that I want to talk about today and lead to the need for distributed algorithms: scalability and decentralization. So scalability has to do with the fact that if you build a multi-agent system with 10 or 15 agents, sooner or later you want to make them 25, 250, 3,000, and combinatorial explosion kills you. So you want to develop mechanisms so that every agent can operate autonomously with local information only, and then you become scalable. Decentralization is connected to this problem. It's really the same thing, but the way that you can argue for decentralization, if you don't care about scalability, is that you don't want to have a single point of failure. You don't want to have a single controller that controls everything. When that fails, everything fails, so you want to decentralize. But in addition to this challenge, which is the one that I want to talk about today, there's also the challenge of communication. If we're going to have multi-agent systems, and they cooperate, they must exchange information at some point in some fashion. And they do that wirelessly these days. We all have this experience with our cell phones and so on. And there's limited bandwidth. More importantly, there's limited battery. That's really the biggest problem of all these technologies. So you would like to move away from the traditional time-driven way of communication where you have a clock that ticks, and with every tick, we all exchange information, and you'd like to move to an event-driven, asynchronous context. And that is sort of a big new trend in systems and control these days. to reinvent everything that we have been doing for decades in an event-driven fashion. The advantage is very obvious. If you can reduce the number of communication that's needed, then you reduce the energy that's involved and the bandwidth. Oh, and by the way, the security, because the less you talk, the less people hear, and the less opportunities they have to jam you or steal information. So this is actually a very important topic. Non-convexity, I alluded to that when I mentioned the coverage control problem. Generally, the interesting problems will not be convex, and in fact, they're violently non-convex, even for very, very simple problems with one or two agents. I can show you examples where you have multiple local optima, and it's really, really hard to find the global optimum. So this is a big challenge. And finally, we live in the era of big data. And therefore, we would like to develop mechanisms which are data-driven. We'd like to move away from the challenge of having developed very elaborate models with model identification schemes and so on, do away with that and get data and then do our control by essentially bypassing this detailed modeling challenge. And we can do that. There are many data-driven methods, and actually I will talk about some of them today and tomorrow. But mostly, this is the topic that I want to cover. So let's focus on the first class of problems, the easier ones, the parametric optimization ones, where all you want to do is you want to position your agents in some optimal way to achieve a certain objective. So I simply copy here what is the general form of these problems. You'd like to solve for a vector S, which will maximize this objective function, which again would like to achieve the best possible cooperative behavior. This is the weight that you put on points in your mission space, and this is the interaction between your agents here and a point subject to some constraints. And I remind you that at least from the coverage control problem, we would like to work with this non-convex function, which captures the joint event detection probability, where these are the functions that correspond to the ability of each individual agent I to detect, if it's positioned at Si, information from points X. I put a hat here to show you that because I have obstacles in the environment, I may not be able to simply sort of spread my wings out there and try to collect information based on distance alone, because, for example, this guy right here is stuck behind this obstacle, and even though his sensing range is this large, there's nothing that he can sense in here because it's an obstacle. So there is a jump here, a jump which depends on the visibility region of a sensor. So in this case, this is the sensing range. Delta I is the radius of this agent, and you can see that he can sense everything in the environment. This is another agent which is partially blocked. This is the overlapping area between the two agents, which captures cooperation. So points in here may be directed by either one of these, and that's the cooperation factor. And here's a guy who's stuck out here, and as you can see, this point over here, for example, is not visible by this particular agent. So this is the kind of functions that we have to deal with, and there's a notion of neighborhood that emerges. So here, these guys are neighbors, because they're close enough to satisfy this condition. These two guys are obviously not neighbors. So decentralization means what can I do based only on my local information and information that I can get from my neighbors. That's really the definition. When can you achieve decentralization? This theorem, we call it the Decomposition Theorem, gives you a sufficient condition for doing that. It says that if these functions, the functions that capture the interaction between the agents and the environment, can be written as a function only of the local reward functions, so the individual sensing ranges, then for any agent I here, I can take my global performance criterion and decompose it into two parts, two functions. A function that depends only on neighbors and myself, and a function which depends on the states of everybody else who is not in my neighborhood. If I can do that, you can see why I can decentralize, at least with gradient-based algorithms, because I can take the derivative of this, and this says this the derivative of this is equal to the derivative of that with respect to SI. So everything which is not in my neighborhood is irrelevant. That's why decentralization is possible. And you can see that, for example, functions of this type are very easy to see, that they are by construction, they're just a product function. They're built to be functions of the local capability of an agent. So problems of this type, with these types of functions, are natural for decentralization. In fact, they're not hard to decentralize. And that's what you can achieve. Then, once you can determine your derivative of the global, the whole objective function, depending only on what you know about the neighborhood, then you can simply use a standard gradient-based algorithm, all sorts of algorithms, not just gradient-based, but based on directions. And there's been a lot of advancements made in this area. This is one of the simplest gradient-based algorithms that basically says, if this is your current solution to the problem, your current configuration of agents, then move to a new one proportional to the value of the derivative, the sensitivity of moving in a particular direction, and under standard conditions, ultimately you will converge and find the solution. So this theorem right here gives us really the key to decentralizing these parametric optimization problems. This is an example of such a problem, which is actually interesting. This is a maze. So this is a wall that defines a maze. And what you like to do is you like to deploy, I think, about 10 agents that are all thrown in from here. And you like them to completely autonomously, in a completely distributed fashion, move around and cover the entire maze. You see why this is hard? Because there's these walls that are obstacles. So as I'll let it run this for a while, because you'll see the emergence of local optima. It's very easy to get stuck into local optima. So far, the algorithm is working pretty well because basically the front guy keeps on seeing open area there and says, well, I have an incentive to move. That means that he opens up space behind him. Another guy is doing that. But look at what's happening here. There's 3 guys, and now one is escaping, that are sticking together because they say, hey, we're doing a great job. Remember, purple is really good. So there's a trade-off between finding a local optima because you do very well locally, but you do lousy elsewhere, and you can get stuck there. And it's very easy to get stuck. In this particular algorithm, we're able to escape this, and I'm not going to go into details of how we do that. And if I let this simulation run for a longer time, you'll see that eventually this guy would go all the way in, and they will be able to do quite well. And you can't see this number very well, but this is the performance criteria.
So there is no communication between them.
Locally, only locally.
Yeah.
Yeah. So, for example, this guy cannot communicate with this guy. Clearly, he can't because you can't talk through walls. This, yes. And again, it looks like they're stuck there. Eventually, they will break away because of some little tricks that we've put in. But generally, it's very hard to. Actually, I can't prove that I have a global optimum at the end of the day. But you hope that you have. And look again. If I don't play some tricks here, I may be stuck here. And clearly, this is not good because these guys cover very well this small area, but there's all this white stuff here that still needs to be covered. So these are difficult problems. Okay, eventually they break away. Okay, it's hard to decentralize problem 2. When you start moving around and you have mobility, so you have graphs that are time varying, and you have to interact with the whole environment, it stands to reason it's very hard to decentralize because I'm supposed to use local information only to do something smart about something that may be outside the doors of this room about which I know nothing. So unless one of my buddies from the team somehow conveys some information to me, but if he's too far away, he's not in my neighborhood. How am I going to do that? It's really hard. So we are going to try and see how we can solve this problem for a class of these multi-agent problems, which is known as the persistent monitoring problem. And in the persistent monitoring problem, you try to find trajectories of your agents so that the agents can achieve a maximal reward interacting with a mission space by essentially monitoring every possible point. So they have to move around constantly and visit all points at all times. That's the idea. So if I want to monitor persistently this area and I can't see very far, I'd have to constantly walk around in some pattern and constantly look at each one of you and see what you're doing. So that's the idea. So if you want to solve this problem in the context of, and it fits in the setting that we talked about, but now I'm going to break it down into physical components. So I need three things to solve these problems. First of all, I need a model for the environment. And if I start with my general problem here, remember I have a time dimension because now I need to move. R of x is the model that I need. What do you know about each point x? How much do you care about each point x? Does point x have dynamics? I need to know that. Then I need to have a sensing model, because the sensing model is what is going to tell me how I interact if I am one of the guys in this vector here, all of the agents, who interacts with a point x. And I need a model for the agents. So I need a mobility model, a motion model, which might look something like this. Okay, let's look at each one of these three things separately. But before I do that, let me give you an intuition why this is a hard problem. So here, if I have all of these, let's call them targets, and so you want to monitor these points. If there are no targets, then you have to monitor everything. But if you have these points, basically you'd like to move around in these trajectories and keep on going around and make sure that you return frequently enough so that you don't lose track of what's happening here. The simple animation shows you an example of how this happens, and you can see the cooperation. Look at this agent, look at this target over here. He gets visited by the purple guy who moves this way and by the yellow guy that moves this way. So that's an example of cooperation. The bars that you see here roughly tell you how long it's been since the last time that you visited. So that's what you're trying to keep down. You'd like to, on the average, keep these bars down. If, for example, if one of them goes to infinity, you're going to be unstable. It means that you've lost track of a target because you're not going back to it frequently enough. So that's the kind of problems that you want to solve. But in this picture, I'm going to show you why these are hard problems. See, originally, you start with a network of agents, the blue one, and that's, for example, the consensus context. And that's kind of easy. It can be hard, but it's just one network. So that network, in our context, first of all, becomes time varying. Why? Because these guys move around. Now they stop moving. They move around, so the context of neighborhood changes all the time. So that alone creates a complication. But then you also have a network of targets. The targets may be connected in some fashion. And then you have a network which connects agents to targets. So for example, I'll return to this later. Let's see, this agent here can only see this target. This target may be seen by two agents. This target can only be seen by one agent. So you really have three networks. The agent network by itself, the target network by itself, and the agent-target network who sees what. And you have mobility, so you have a time-varying structure. So really, it's kind of hard to keep track of all of this. And you can see how decentralization is hard. What do I know about this target if I'm this agent? Nothing. The only thing that I might learn is through this guy, who is the only guy who can ever do anything to it or see something. So somehow I have to hope that information from this interaction trickles down to me so I can do something. And it doesn't look like a decentralized approach might work. So that's the challenge which I'm pointing out here, and I will return to that and see how we can do it. Okay, so going back to what I said, there are three kinds of neighborhoods. There's the agent neighborhood, and you can see this example, A1 has three neighbors. There's the target neighborhood of an agent. So for example, this agent only has one neighbor target. And then there is the agent neighborhood of a target. So these two agents are neighbors of the target. All of these have to be taken into account. Okay, so now let's go back to the persistent monitoring problem. Let's start with it in a one-dimensional mission space. Yes, you'll argue this is limited, so this is just a segment on the real line. But we'll learn from the one dimension before we go to 2 or 3 dimensions. And I would also argue that actually there's a lot of interesting one-dimensional problems. For example, in smart cities, there are streets. So if I want to monitor what's happening in the street, I can only move up and down along the street. Rivers, canals, water facilities, they're one-dimensional conveyors of fluid. So I can only move up and down in the river. So one-dimensional problems are not to be just toyed with alone. They are interesting enough. Okay, so as I said, I need agent dynamics, I need environment dynamics, and I need an interaction model. For the agent dynamics, we'll assume that we have this very simple single integrator dynamics. So all I'm controlling is my speed. Because I'm in one dimension, that means I can only go right or left or not move. However, I will point out that the analysis is general enough that I could go to a nonlinear model as long as the nonlinearity is contained only in the state, not in the control. But that's just an aside. Okay, so here's a picture of a one-dimensional mission space. Here's two agents that move right or left. This is supposed to indicate their sensing range. So let's assume that they have kind of like the ability to sense, if they're here, everything within a range, but with monotonically decreasing capability. So point X falls in here, so I can see it if I'm this agent pretty good. I can't do it from here. So this gives us a sensing model, which is captured by this function, the probability that agent S at S senses point X, and you can choose your favorite model as long as it's a monotonically non-increasing function. The environment model. Now I have to indicate how I'm going to interact with any point X, and I'd like to put some dynamics on X. So I don't know what X is exactly, but I do know that if I haven't visited X for a long time, that's pretty bad. And so I will attach an uncertainty function to it. And the dynamics of the uncertainty function look like this. So if you ignore this for a minute, imagine A of X as just being an uncertainty input into the point X. So it keeps on increasing uncertainty until I am close enough to reduce the uncertainty. So I am collecting data. So more data are being dumped at this point, but I'm able to collect them somehow. And depending on the configuration of these two agents, I am able to do that effectively or not. And this 0 is there because I can't go negative. I mean, if I have learned everything there is to be learned about this target over here, we say the uncertainty function has reached 0, and I cannot go negative. So these are the dynamics of every point X. And if I happen to know more about X, then I will have a more detailed model, which might include some dynamics. But for now, we'll just limit ourselves to this simple uncertainty model. This is a simple picture to tell you what this model essentially does. For every known target point, these are these uncertainty inputs, so this dumping uncertainty, this uncertainty fluid. And what your job is to run around and trying to empty uncertainty. And you can see that if you don't do it right, this uncertainty will keep on increasing too much. So you may increase this to infinity while you're paying attention to these guys. So you have to constantly run around to do that. And again, we're going to use this joint event detection probability for this function over here. So if I have two or more agents who are close enough to a target, in this particular case, this agent looks like he can monitor both of them. Then you can empty the uncertainty as much as you can. Okay, so here's the optimal control problem that I formulate. I am going to try to minimize the overall average uncertainty. So all these uncertainties of these targets going up and down, I'm going to try to keep it as low as possible, subject to the agent dynamics here. I may have constraints on the agent dynamics. I certainly cannot go left of 0 to the right of L, but I may even have some constraints that don't allow me to move too far to the right, too far to the left. And these are my target dynamics, so over here, which are measured in terms of these uncertainty functions. And the sensing model that I'm going to include here can be really any function, any sensing model, but we use sort of a linear decay. Just the math is a little easier that way, but it's not very important. And this is the range. We also assume that there's always a finite range to make the problem more interesting. All right, so here are things that we can prove analytically. Number one, that the optimal trajectories are bounded. In other words, it turns out that every agent J optimally will move between 2 points, x1 and xm. It has no incentive to go outside these 2 points. What these points are, I don't know. Number two, there exist points in the trajectory of a target where you will dwell someplace, presumably at the target, for a finite amount of time. So being at rest is part of the optimal solution. So not only do I have to worry about how far to the left or to the right I have to go, but I also have to worry about how much time I spend at rest, presumably emptying this uncertainty bucket for a finite amount of time. And also you can prove that on an optimal trajectory, if you order your agents in a certain way because it's one-dimensional, there is no incentive for them to cross, right? So this is not part of the optimal trajectory, which is nice because you don't want your targets to cross each other, and then the roboticists will also tell you, oh, what about collision avoidance? How do you do that? You say there's no collision avoidance issue because collisions are not optimal, so I'm going to eliminate them. So these analytical results are good because they allow us to reduce what is a dynamic optimization problem, a hard optimal control problem, into a parametric one. Because obviously, the only thing that an agent does is it moves between two endpoints. So if I could find all of the endpoints that we call the switching points for each agent, and I could also find the times that an agent must wait at certain points, I'm done. So my entire optimal control problem is parameterized by these two parameter vectors, and I can reformulate the dynamic optimization problem as a parametric optimization problem. And this is called an event time because the whole trajectory is broken down into a bunch of events. An event is where you stop at rest and then you start moving again, either to the right or to the left, or whether you switch. So the whole dynamic optimization problem boils down to a parametric optimization problem. This is huge because we know how to solve parametric optimization problems efficiently. We don't know how to do it in dynamic optimization. We do, but the curse of dimensionality will get us. So graphically, this is basically what these guys do. They're oscillators. So your job is to find the endpoints of this oscillation, and also in between, they may stop for a certain amount of time, and you have to find that optimal time too. And therefore, the whole system here is a hybrid system, and we know a lot about hybrid systems, meaning that its whole trajectory can be decomposed into pieces that correspond to events. What do I mean by events? I mean really points at which the dynamics of either my targets or my agents jump. So every time you see a jump from -1 to 0, that's an event, which means I have to define all the events in the system. There's a lot of them, and the notation can get hairy, but I'll break it down for you. It's not too bad. There's two events here, which correspond to when you jump from 0 to something non-zero. There's two events here, which have to do with the sensing function. So somewhere in here, at some point, you exit the range of a sensor, or you enter the range of a sensor. That's an event, and that's going to turn this function over here to something which might be 0 to something which is positive. There's these events which have to do with the change of the neighbor sets. Remember, because the agents are moving all the time, the concept of a neighborhood changes all the time. But the minute there are some discrete points in time where an agent becomes a neighbor of another agent, or a target becomes a neighbor of another agent. So you can define those as events. And then there's all these events that correspond to these jumps in the agents. There's 4 of them when you jump between -1, 0, 0, 1, and so on. So those are my events. Moreover, I'm now able to differentiate my events between local and non-local events. So these are target events, and these are agent events. And you can see that if I'm an agent, obviously I know all of my events. And if I need to know some events about a target, I can, as long as this target is a neighbor of mine. So that allows me to define the concept of neighborhood, hence, what does it mean to be decentralized? So this is just a simple example for one agent or one target, just to show you what are the events that I'm talking about. I'm talking about events for jumping this way, or for example, events when this becomes 0, the uncertainty bucket empties, or ceases to be empty. These are the events that I care about. So, returning to this parametric now optimization problem, all I have to do is find the gradient of this function over here, and then go to my gradient-based algorithms. So this is where infinitesimal perturbation analysis, or what we call the Ipa Calculus, comes into play. And I have about 10 minutes or so, I think. So I'm going to go through this Ipa Calculus very, very quickly. But once you buy into it and understand it, then you can get estimates of this gradients over here and plug it into your favorite gradient-based optimization, and have a solution. So here's where I'll open a quick little parenthesis to tell you about the Ipa Calculus. The Ipa Calculus has to do with data-driven, so I promised that I would talk a little bit about data-driven optimization. You have a system, any system with noise. You're trying to maximize and some expectation of its performance because it's generally a stochastic system, and you're trying to do it with a parametric control. So I'm trying to adapt the controller with respect to some parameters in order to get the system to minimize or maximize its performance. I'm going to do this by observing the system state and my performance, subject potentially to more noise, by estimating this gradient and essentially closing this loop and do what you might call adaptive control. And this happens with real-time data. So this is why this is data-driven. I'm just collecting data from the system, learning from the data, and updating my gradient to do better and better. And of course, this is easier said than done because, first of all, obviously, if I knew what this function is, then it's a simple problem, but I don't. So I'm dealing with an unknown expectation here that I have to estimate. Well, I'm not estimating it. I'm actually estimating its gradient, okay, through the gradient of the sample function of what's inside. And then there's the statistical issue. All right, if you can estimate the gradient of what's inside the expectation, who says that the gradient of the expectation is actually a good one? So there's an issue of unbiasedness here. But never mind that. For the class of what we call discrete event systems, so if your systems are discrete event systems, so basically they behave in this way or they satisfy some kind of an automaton model, then we can do that, and this is what's called IPA. So the question is, what about hybrid systems? Systems which in general satisfy different dynamics as they move from event to event, and the question is, how do we do that? Well, we can do it, and if we can do it, then we can get these gradients of these expectations, plug them into these gradient-based algorithms, and we're done. So I'll just give you the Ipa calculus, which comes down to 3 equations. So that's why we call it the calculus. It's like, whenever you deal with some kind of a mathematical framework, like let's say Kuhn-Tucker conditions. You learn what the Kuhn-Tucker conditions are, and then it becomes a recipe, and you just solve problems. So that's what we're trying to do here. Give you a recipe that you can use and just simply plug it into your problem. So the only notational thing that's important is that the prime notation means derivatives with respect to my controllable parameters, as opposed to dots, which mean time derivatives. And these are the derivatives, the sensitivities that I'm interested in. Sensitivities of my state with respect to the controllable parameter, and sensitivities of the event times with respect to my controllable parameters. So very quickly, the first equation has to do with what happens at an event to this derivative. And it turns out that you can write it in this very simple fashion. What happens after the event is what happens before the event, plus this information, which you know because it has to do with the dynamics of your system before the event and after the event. And this is the sensitivity of the event time. That's if the state is continuous. If the state is not continuous, then you must know something that is in hybrid systems is known as the reset function. You must know how the state resets, and actually it's an easier problem if you know the reset function. This is equation number 1. Equation number 2 has to do with what happens in between events. Well, it turns out that with simple differentiation, you can come up with a linear differential equation in these derivatives, and you can get its solution, in which you see that I can get the sensitivity of the state in between events based on things that are computable, plus an initial condition which comes from equation 1. And then the last part is what happens to these event time derivatives. Well, there are events which are so-called exogenous, which means they don't depend on the controllable parameter, so that's 0. There are events which are called endogenous. Those are the ones which basically correspond to what are known as guard functions. You hit a guard, switching function, and then, of course, you change dynamics. In which case, if the switching function is known, and it better be known if you have a model, then again I can compute this. And then finally there's another class of events that are called induced events, but don't worry about them. So if you ignore those, the Ipa calculus comes down to these 3 equations, which graphically work like this. You wait until you see an event. When you see an event, you apply equation 1 to see how the state derivative changes. But to apply equation 1, I need this derivative, which comes from equation 3. So the combination of equation 1 and equation 3, whenever you see an event, allows me to compute to update my state derivative. Then, equation 2 is used to propagate the state, and then you repeat, and that's it. So, there are 3 properties which are important. Let me just skip to that. If you compute the derivative now of your objective function, it comes down to depend on a component which is only what happens at events, and a component which gives you what happens in between events. This is a mess, because this is an integral which may have to be numerically computed. This is easy. This comes from one of the equations. This is something which is directly observable. It's what my performance is at this time. So, there is this theorem that basically says that under some very general conditions, this doesn't matter. And the whole sensitivity question, the gradient of what I'm looking for, comes down to these very, very simple expressions over here. So, this is what we call robustness. It doesn't matter what your system is doing in between events. It's only what happens at events that matters, and this is under certain conditions. So let me just skip that. The second property is what we call decomposability. Depending on the nature of the switching function, you might be able to actually break down a trajectory into separate pieces and study them independently, which simplifies things. I'll skip that. And the third, scalability. This is where event-driven comes in. Notice that the entire Ipa calculus is event-driven. All I do is I wait until a certain event, I do something, and then I jump to the next event. That's event-driven. That means that the entire process here scales with the event set, not the state space. You can keep on increasing your network until it explodes, but it scales with just events. So with every new dimension that you add to your problem, you add a few events, which is typically a relatively small set, and you scale with the event set. This explains why you can use this approach with a network that may become very large, but as you explode in the state space, you don't care because your control is reduced to just an event space. So this is very important property. So, coming down to my problem, using the Ipa calculus, I can use these 3 equations, applying them to my persistent monitoring problem. I can then obtain these gradients over here. I will not give you the details. I will just simply, again, say, use these 3 equations, put them on a piece of paper next to you, fit them into your particular problem, and as long as you know how to differentiate and integrate, you can do it. For just about any problem that we've ever faced. I haven't really come up with any problem where we could not do that because of other technical conditions or anything like that. So it's very, very general. This is an example of what happens when these 2 events occur, 2 of the events that I mentioned. You get an equation which is very, very simple. You get a gradient which either doesn't change or resets to 0. And so you see that sometimes out of all this complex math, the final results can be extremely simple. And then for in between the events, you get these equations, which admittedly they look a bit complicated, but they're not really. This GI that you see here has a nice physical interpretation. It's a function which captures the cooperation. So the sensitivity, the derivative here that you see depends on the cooperation factor. So you can see that it's very pleasing intuitively. It says the more cooperation I have, the more this derivative is going to be amplified, and the less cooperation I have, the less so. So there's very nice intuitive interpretations to all of these. And when the dust settles, this is the kind of solution that you get. So in this case, I have an agent which moves right and left and tries to empty these 3 uncertainty buckets. These are the trajectories, and these are the simulations. It's easier to see. So in the single agent case, you see what this guy does. He moves right and left and stops for a certain amount of time at each target to get it to empty. In this case, these 2 guys apparently split the space. So this guy takes care of these 2 targets, and this guy takes care of these 2 targets very effectively. As you can see, they hardly can go up. That's because they're so close. All he does is he moves between them almost doesn't move and keeps them completely under control. And these are the kinds of solutions that you get in 1 dimension. Now, as I said, this was centralized. Can I decentralize? And I'll try to sum this up. Because of this Ipa calculus, because of the fact that my whole solution depends on a gradient, really the problem of decentralization comes down to, can I evaluate this gradient using only local events? Is it true that these calculations that I did here depend only on local events? The answer is no. They do depend on global events, but I'll skip this because I'm running out of time. I'll show you the key result, which is this. The key result says that this gradient over here, okay, when it involves non-local targets, so targets that I cannot really see, but I need to obtain to this gradient, okay, this, because of this equation, this only depends on this event. This is the event which says your target has now emptied out of uncertainty. In other words, you have emptied all the uncertainty, but it does not depend on this event, which is the event that says, okay, now the uncertainty starts increasing again. So I only need one non-local event, this event. I need to know when a faraway target has been emptied. But of course, if it's been emptied, it must be because there was an agent there. Therefore, all I need to do is communicate with that agent. Now again, the agent may not be in my neighborhood. If he's in my neighborhood, I'm done. So this is why we say almost decentralized. There's just this one event. Every once in a while, this event is out there that is not local, and I need to know it. So only one global event, non-local event, affects the gradient. So if I could, for example, depict this here, if you look at this target is not seen by the agents except for this guy. When this guy is there and brings down the uncertainty to 0, that's an event, he needs to communicate it to A2. That's the only neighbor. If then A2 communicates it to the rest of us, then we will be able to do the almost decentralized control. So the almost comes from the fact that if I'm this agent over here, I can do everything I need with local information except for what happens with this particular target over here, and I need A4 to help me. So in that case, there must be a delay, basically. And that's what this theorem basically says, that you can recover the entire centralized solution. Remember again, what I mean by decentralization, I mean reproduce the centralized solution with only local information. You can do it with only local information, but you do need this annoying non-local event that I need to get. And this is an example of what happens when you use this almost decentralized algorithm. You get this cost, this performance, but cost actually I'm trying to minimize, but if you ignore the non-local events, you get a worse performance, obviously. So this is the price of decentralization here. This is interesting because it says that decentralization does not necessarily mean that I have to estimate and reproduce the state of the faraway entities in my system. That's the naive way. Decentralization means that if there's something far away, I need to reproduce its state, to estimate the state. But that's not true. And this is captured here because the red is the true state of the target, but I don't need it. All I need to do is capture the green dots that you can barely see. These are the events when I need these non-local events. So I don't need to recreate an entire function. I just need to capture a few key points of this function. So that's really the message. You can decentralize even these hard problems almost. What do you do when you go beyond 1D? I'll simply show you here, for example, that in 2D I need to now create trajectories. So this guy now is running around trying to visit, as you can see, all of these targets and keep them down as much as he can. So this is now I have to develop a trajectory. I can no longer parameterize. Okay? So that's the challenge. So what we're doing is we're saying, okay, I cannot parameterize, but what if I limit myself to sets of trajectories which are parametrically defined and then optimize over these trajectories? That's the best I can do to find optimal trajectories within these families, and that's what we're doing. That's not so far-fetched because it's not a bad idea to create solutions which may not be completely optimal, but they have some nice properties. For example, periodicity. In this particular case, let's see if I can get it to run again. can't get it to run again, but you notice that basically there was periodicity. There was a guarantee that however this guy moved, he would always return to one of these targets. So it's not a bad idea to limit yourself to such optimal trajectories anyway. So if I go into 2 dimensions, I now have more complicated agent dynamics in 2 dimensions. You can see I have a heading that I have to control along with the speed. If I can assume that my trajectories can always be parameterized in this way, then I can essentially extrapolate from what I learned from 1D, and I can prove the same result. I can prove again that the IPA gradient again can be obtained with only local information except for this annoying event. For targets which are not in my neighborhood, when they experience this one particular event, I need to know it. If you can give me this event, which admitted is not local, then I'm done. I can decentralize. And so, in conclusion, decentralization is relatively easy for parametric optimization problems, challenging for dynamic optimization problems. Almost decentralized solutions are possible. If you want to eliminate the almost, fine, but you'll pay a price. And then when you go from 1D to 2D, as long as you're willing to limit yourself to certain parametric families, then you can exploit the properties of IPA and get this done. And this is what I'm going to be talking about tomorrow. This is like, if you're going to the movies, I remember when I was going to the movies, there was always sign that said Avrion. Okay. So this is the Avriani Parastasi. This is where I'm going to try to apply some of the things that I talked about today, but only to the Internet of cars. And how do you control cars in terms of their speeds and accelerations so that you can have them coordinate, eliminate traffic lights, and automate, essentially. And that's going to be tomorrow's topic. Okay, thank you very much.
Any questions? Shy? I'll start with one then. At some point, you assume that you know the targets, right? Where you have all these towers that come down. You assume that you know. Yeah. Doesn't this come down to the traveling salesman problem?
In the traveling salesman problem, it's a version of the traveling salesman problem. But first of all, you have multiple traveling salesman problems. You have dynamics which apply to the cities. So in the traveling salesman problem, you're just going to a city to collect a cost. But here the cost changes. It has dynamics. So depending on what time you get to the city, you collect a different reward. And it's not just one tour. It's really a continuous tour. Okay, so yes, it falls within the family of traveling salesman problem, but there's a lot more components. And in addition, you can put noise. So in traveling salesman problem, you assume the cost is fixed, that's it. But what if there's some stochastic, some distribution on the cost of a city, which there is here? We allow that. So it's a very complicated traveling salesman problem.
Yeah, but that's an example of a very difficult problem.
Yes.
That you're trying to.
Yeah.
Which means that this is even more difficult, and now you guarantee also optimality somewhere.
Compared to the traveling salesman problem, you mean?
Yes.
Yeah, well, okay. First of all, I guarantee optimality in 1 dimension. Okay. In 2 dimensions, I cannot. That's why I say I need to parameterize. If I could parameterize a traveling salesman problem, for example, if you gave me a set of algorithms for a traveling salesman problem, you said, just simply adjust these parameters and you'll find the optimal solution, then we're talking about the same thing. But I can't do that in 2 dimensions. So if you believe the traveling salesman is a graph in 2 dimensions, yes, I can't do that. It's much harder, absolutely. In fact, if you look at optimal solutions, if you solve through dynamic programming or calculus of variations, the optimal solutions look like spaghettis, just all over the place. So that's why I'm saying there's something weird about some of these optimal solutions. I would rather impose some constraints that say you must return to the same target within a finite amount of time and make them periodic. That'll simplify my life.
Is it true that IPA is the same, or this looks like stochastic gradient? And if so, what are the conditions on tau k for convergence? Should it, for example, converge zero non-summably or some other conditions?
Yes. Answered the first question, is it the same as stochastic gradient? Yes. What are the conditions? There's about 12 of them for the stochastic gradient approximation, I don't remember. But yes, you need the summability conditions, the learning rates, the parameters, the step sizes must go down, but not too fast. There's a few others. Lipschitz continuity is what we need from our functions. You need a lot of technical conditions, yes. But assuming you satisfy those technical conditions, then you can prove very easily unbiasedness, which in older days we could not prove for discrete event systems, but for hybrid systems we can. That's really the big breakthrough that happened in the last 10 years or so.
So the result here is that your gradient as well as the parameter estimates converge in probability, right?
No, they converge to whatever your favorite stochastic approximation algorithm converges to. I haven't changed anything to the algorithm. That's why I said use your favorite gradient-based algorithm. Okay. But please note that what I talked about here didn't have any stochasticity.
Yeah, I was referring to the previous actually.
When there is stochasticity, then all these issues come up. Now, here's one of the properties of IPA that I didn't mention. It's robust, I sort of mentioned. It's robust to noise. So I can have the way in which uncertainty enters to my targets satisfy very, very mild technical conditions in terms of the probability distributions, and I can still prove the unbiasedness. The reason is that, of course you couldn't see it, but if you clean up the math, none of the expressions for the gradient depend on these AIs. The AIs were the uncertainty inputs. The IPA gradient does not depend on those. It's robust. So I treated them as deterministic here, but if you treated them as stochastic, you would get the exact same result. This is an amazing benefit of IPA. It's a gift that IPA gives you. Actually, there's no magic, because when I say this, people say, oh, black magic. No. You pay a price, data. Because I have to now observe when each event occurs, that information hides the probabilistic information that somebody else might need. So there's no magic. It's just that it's part of the data.
So I had one question with respect to with respect to IPA. So let's say that you have very rare events. So the events take place very rarely, and this, as a result, it means that your algorithm will converge in
fact, it will never converge. Yeah. Very good point.
So
yes, you're absolutely right.
What can you do then?
Yeah, what can you do? It's a separate talk. We discovered that, we knew that, but we kind of didn't want to worry about it. And then about 3 or 4 years ago, I was facing a problem, and one of my students said, it doesn't converge. And then we, of course, observed exactly what you said. We call it event excitability. You know, like in some of the control mechanisms, you need this persistence of excitation concept. Here you need it. You need to see events. Yeah. If I don't see the events, if my agent doesn't actually get to a target, I have no information, because it's a data-driven method. If they're rare, it's sort of okay, all right, I can see them, but very rare. So what can you do? What you do is, I'll tell you separately, it's lunchtime, you can do something. There's something you can do. You spread the information that's contained in the events, you kind of spread it out so you can always get some information. That's the idea. You pay a price, of course. But that's a very good question, because now, even though we love event-driven and all that, we're now slaves to the events. If we don't see the events, this doesn't work. Yep, good point.
Any other questions?
Could you, on this same topic, could you use artificial events? Pretend like there's real events.
Yeah.
Create events.
So, yes, good point.
Like a node.
The nice thing about event-driven methods in general is that you can define the events that you want. Some events are natural. Failures, the fact that a target, that an agent reaches a target. It's an event. I gotta have it. But yes, I can define virtual event, artificial events, anything I want at a price. I argued that because all these techniques are scalable with the event set as opposed to state space, that's an advantage. So if you now start throwing events into my event set, you will counter my argument. But yes, you can do it.